Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be going over problems 26 through 28 of the Geometry January 2015 released examination. All right, let's take a look at problem 26. It reads, the bases of a prism are right trapezoids as shown in the diagram below. So we can see the two right trapezoids. DACB and ZWXY. Which two edges do not lie in the same plane? Now, one thing you want to note about problems like this involving finding sides that are coplanar is that if two segments are intersecting or parallel, then they lie on the same plane. Okay? If two lines or segments are intersecting or parallel, then they are not skew. Okay? Skew lines are non-parallel lines that never intersect. Another word for line on the same plane is coplanar. Co means together, planar means on a plane. So if two segments are coplanar, then they lie on the same plane. Okay? Now the steps we're going to use to solve this problem is we're going to identify the pair of sides on this right trapezoidal prism. And then we're going to see if they are intersecting or parallel. If they are intersecting or parallel, then the sides are planar. They are not skew. But if they um, are not intersecting and not parallel, then they are not coplanar and they are skew. Okay? All right, so let's take a look at it. So it says, let's take a look at BC and WZ. So segment BC is this segment going up and down right here, and then WZ is back there, that segment. Now, are these, if we put a line on these two segments, we extend them, are they going to intersect? The answer is no, they never intersect, okay? That distance between these two, the height of the trapezoid will be the constant distance between um, a plane that's containing both lines as long as the plane is perpendicular to this line right here. Okay, so they are not intersecting. Are they parallel? We can clearly see that they are not parallel. Now, since these two lines are not intersecting and not parallel, then they are not on the same plane. They are skew lines, skew sides. Okay, so let's go ahead and write that down. For option number one, side BC and WZ, okay, are not parallel and not intersecting. They do not intersect. Do you know what that is called? If two sides are not parallel or intersecting, that basically means that they are skew lines. Okay, so that's the indication here. They are skew lines. All right, so since they are not parallel and not intersecting, aka skew, then they are not they are not on the same plane. Okay. All right, so that's the answer we were looking for. Our answer is option number one, the two sides that do not lie on the same plane. Now I'm going to go over the remainder of them so you can really understand the whole idea of coplanarity and skew lines. All right, number option two, we're looking at sides AW and CY. Now, AW and CY, let's take a look at these two lines. What do you notice about them? AW and CY. These two lines are parallel. Okay? So if they're parallel, you can see that you can draw a plane that goes through both of them. It's basically like the diagonal of this trapezoidal prism. So AW and CY are parallel. So what does that mean? They're parallel, hence they are coplanar. Hence they are coplanar. Remember, in order for two sides to be coplanar or to lie on the same plane, they either simply have to be intersecting or parallel. One of the two will suffice. Okay, in this case, parallelity enabled us to conclude that the two sides are on the same plane. Okay, all right. Now let's take a look at option number 3. We're looking at sides DC and WX. Number 3, side DC and WX. What do we know about these two? Are they skew lines or not? DC is this side right here, DC, upper left corner, and then WX is that side over there. Now, what do you notice? These two lines are parallel. Since they're parallel, they're not skew. They are on the same plane. Okay, they are coplanar. Let me draw the plane for you so you have that nice little plane right there. Let's make this a dotted line. And then this one can go over there. And if you want, you can extend the plane so that you see that plane that fits perfectly through it. Okay, so you see that's the plane that contains the two sides. The fact that they're parallel is sufficient for us to conclude that they are coplanar. Okay, so segment DC and WX are parallel, hence what? They are on the same plane, on the same plane. Do you know what it means to be on the same plane? Another word for that? Coplanar. All right. Okay. Option 4. Do they lie on the same plane or not? Segments BX and AB. BX and AB. All right, let's take a look at that situation. Let me use red lines here. So for that one, we have BX is at the base right here. So this is side BX. Let me just extend it so it's obvious. So side BX is there, and we have side AB. Let's draw that. Side AB is this side right here. Okay. Are these two lines parallel? No, they are not parallel. Does that mean that they are skew lines? The answer is no. You notice that they intersect at a point. Remember, skew lines are not parallel and not intersecting. Okay? Any two lines that intersect, if any two sides intersect or any two segments intersect, then they are coplanar automatically. Okay, so they intersect at point D. So what do we conclude? BX, side BX, and AB are intersecting. So what does it mean if they're intersecting? They're intersecting, hence they are what? They are coplanar. Hence they are coplanar. So don't forget the condition for coplanarity. Okay, there's just two. If the two sides intersect, they're coplanar, or if they are parallel, then they're coplanar also. All right, but this problem asks for the cases that where the two sides do not lie on the same plane. So we're looking for cases where they're not coplanar. So our answer is option 1. The other ones are wrong because they are coplanar segments or sides. All right, let's take a look at problem number 27. It reads, in the diagram below, segment A prime B prime, the segment right here, is the image of segment AB under which single transformation? Now, one thing you want to note about this problem is that a glide reflection, option 4, is a composite transformation. It is a combination of reflection and translation. Okay? All right, so the step we're going to use to solve this problem, we are going to compare these two uh, segments, the original one and the image, and we're going to see which of these transformations can produce this image from AB. Okay. All right. So let's take a look at what we have here. Dilation doesn't really apply here because if you notice, this is 3 by 3 and this is 3 by 3, so they have exactly the same length. It's not any bigger or smaller. Translation involves just moving this line. Okay, so let's just draw a segment. Let's say this is segment AB. Translation of AB just involves moving AB. Let's see, let's try and make this work. Just involves moving AB up and down. So moving it up and down or side to side. Okay, that's the translation. Vertical or horizontal. Now, can you get this image by just moving it up and down or side to side? The answer is no. Okay, so this clearly a is not just a translation. There's something more going on here. Now, how about a rotation situation? If I rotate this figure AB, will I get this right here? Okay. If I rotate it, let's see, probably 180 degrees, the orientation is going to be different. Let me show that to you real quick, just to help you see that this is not a rotation, okay? So what I'm going to do is notice how AB is right here. If I rotate AB uh, 90 degrees, that's 90-degree rotation, does it look like this? The answer is no. If I carry out another rotation, 180, what I was talking about earlier, would be on top and A on the bottom. What do you notice about the orientation of these two? Do they look identical? Let me see a little bit. Does this right here, does it match that? The answer is no. Even with a 270-degree rotation to the horizontal like this, it kind of looks close, but you notice the orders are reversed, and this is strictly on the fourth quadrant, whereas this is on the third and fourth quadrant. So we see by rotating segment AB, we do not get this image. Now, what if we do a glide reflection? What if we combine a translation with a reflection? Can we generate A prime, B prime? So how about we do a reflection first? If we carry out a reflection, along the x-axis, it's going to take us right here. All right, so that's a reflection of AB. So you go 1, 2, 3, 1, 2, 3. The reflection of AB along the x-axis. Now, what if we shift this segment 3 units, 1, 2, 3 to the left? Bam. We get this right here. It's exactly what we want. Okay, so what does that tell us? It tells us that this image is a glide reflection. It is a combination of reflecting this line along the x-axis and shifting it 3 units to the left. Okay, all right, so let's go ahead and write down what we just talked about. So let's start with dilation. Option 1. Is this a dilation? So dilating segment AB, um, does that yield segment A prime B prime? Is it possible? This is false. It's not possible because um, in this case, AB, the length of AB is equal to A prime B prime. There's no dilation happening, okay? It wasn't stretched, and that, apart from the fact that their lengths are the same, their positions are totally different, okay? So we see that it's not a dilation. And we also have to state that and A prime B prime is in a different quadrant. So there's some kind of translation going on here. Okay. All right. Now how about option 2, which is rotation? Option 2 rotation, can we say that if we rotate segment AB by um, an angular measure, let's say theta, that is going to yield segment A prime B prime? Can we say that? This statement is false. Why? Because rotating segment AB never yields A prime B prime, okay? So no matter how you rotate it, you're never ever going to get the image A prime B prime, segment A prime B prime, because it's not a rotation transformation. All right? Now how about translation? Translation. Can we say that the translation um, by some vertical and horizontal unit on AB alone can yield the image A prime B prime? Is that possible? This is false. For the same reason as 2, because simply shifting, only shifting, that's what translation is, only shifting AB up, down, or left, right, up and down, vertically or left and right, never yields the image A prime B prime. Okay, so we see it's not a dilation, rotation, or translation. Our concluding answer from what we talked about earlier was that this situation is a glide reflection. How is that so? Let's go ahead and take a look at that as a glide reflection because it is a composition of a rotation about the x-axis, compose that. Well, let's switch the order here. So if we, yeah, still going to be the same thing. So let me stick with the order that I did during our conversation earlier. So we did the transformation last. So the composition of transformation, -3 means 3 units in the x direction, which is 3 units to the left. If you compose a 3 units to the left shift with a reflection about the x-axis, guess what? If you carry out this composite reflection on segment AB, it yields A prime B prime perfectly. Okay, we showed that earlier. So this statement is true. Why? Because reflecting AB about the about the x-axis and translating it or shifting it, translating it 3 units to the right left, as we see here, 3 units to the left. Guess what happens? It yields our image. All right, it yields A prime B prime, segment A prime B prime. Okay, so composition of two transformations is known as a composite transformation. In this case, translation and reflection are known as glide reflections. All right, let's take a look at problem 28. It says, for which diagram is the statement triangle ABC is similar to triangle ADE not always true? So one thing you want to note is that in order to show that two triangles are similar, you have a postulate and two theorems that can be used to arrive at that conclusion. We have the AA angle similarity postulate, which states that if two corresponding angles of two triangles are congruent, then those two triangles are similar. We have the SSS and SAS similarity theorems. SSS means all three corresponding sides are in proportion, and SAS means that two sides um, are in proportion and the included angle of those two sides that are in proportion are congruent, then the two triangles are similar. Okay, so just note that the s's in the similarity theorems do not represent congruence, they represent proportionality. Okay, all right. Now, the steps we're going to use to solve this problem. First of all, we're going to basically take a look at the triangles and label the congruent sides that we know accordingly, and then see if the information provided matches the AA similarity postulate or the SSS and SAS similarity theorems. Okay? All right, so let's start with option number one. So for option one, the question is triangle ABC, is it similar to triangle ADE? Okay, so notice that we have different sets of triangles here. Even though their labels are similar, we have to be careful not to assume that it's talking about the same thing over and over again. We have to follow the labels and make sure we are examining the correct triangles. All right, so this is pretty straightforward. A, B, C, and ADE, are they similar? That's the question. Well, we know that these two angles are congruent, so we know that angle ABC is congruent to angle ADE. That's a given. What else do we know? Well, these two triangles share the same angle. Okay, so they both share this angle right here. So what can we write? We can also conclude that angle BAC, oh snap, wrong color. Angle BAC from the bigger triangle, angle BAC is congruent to angle DAE. How do we know that? They're the same angle, the same angle. All right, now that we have two angles that are congruent, guess what? We have the AA situation. If two triangles have two identical angles, what can we conclude? They are similar by the AA similarity postulate. Okay, so triangle ABC is similar to triangle ADE by the AA similarity postulate. Okay, all right. Let's take a look at number two. So number two, let's look at this. Well, we have a lot of triangles going on here, so we have to be careful. In this second situation here, it looks like a parallelogram. Is triangle ABC similar to triangle ADE? Still asking the same question. Now, if you take a look at this triangle, triangle ABC, we have this triangle right here, and triangle ADE. This is interesting because we see these alternate interior angles. This is congruent to that, and this is congruent to that. This is also congruent to that because they are vertical angles. So we have three A's, but that's an overkill. We need just two A's to conclude similarity. Okay, so we're just going to go ahead and state that two are congruent. So triangle ABC, I'm sorry, angle ABC, this triangle right here, ABC, this angle with one tick mark, is congruent to the corresponding angle on the other triangle, ADE. How do we know that? It's given. And then we also know that angle BCA, the one with two arcs, is congruent to angle DEA. So I said angle BCA and angle DEA. Yes, angle DEA. They're also congruent because that's a given. All right, what do we have here? We have A angle A. What does that tell us? The two triangles are similar. Okay, so triangle ABC is similar to triangle ADE in option number 2 by the AA similarity postulate. All right, similarity postulate. Okay, let's take a look at the next candidate, option number 3. So for option 3, we're still asking the same question. Is triangle ABC similar to triangle ADE in this situation right here? So if you take a look at this situation right here, we have two right angles. That means you're congruent. And we also have a vertical angle here. So the vertical angle in angle EAD is a vertical angle with angle BCA. So these two are going to be congruent. So we have AA also. Let's go ahead and write that down. For number 3, um, we have, let's see, we have to answer the question by stating that angle BDA is congruent to angle CBA. All right, I'm looking at the 90-degree angle. So EDA is a 90-degree here, and then CBA is a 90-degree there. They are congruent. How do we know? It's given. All right, and we also know that angle EAD is congruent to angle CAB. Okay, CAB. Why? They are vertical angles. Vertical angles. Okay, so what do we have here again? We have an AA situation again. AA, what does that mean? They're similar. AA is sufficient to conclude that two triangles are similar. Okay, so triangle ABC is similar to triangle ADE in case 3 by the similarity by the AA similarity postulate. Okay? All right. Now, let's take a look at um the fourth problem number option number 4. Let's see. Same question, is triangle ABC similar to triangle ADE in this situation right here? Oh, we're given the fact that angle BCA of triangle ABC is congruent to EAD. All right, so let's write that down. We know that angle BAC is congruent to angle EAD. That's a given. What else do we know? Uh-oh, that's it. That's all we know. So what do we have here? We have A. Okay? So does this match any of the postulates or theorems? The answer is no. We either need to have AA, SSS, or SAS. We just have A, that's not sufficient. It's not sufficient to conclude that two triangles are similar. Okay? So let's go ahead and write down the remark that shows that that's the answer. We just simply say that triangle ABC is not similar to triangle ADE because there is no A similarity theorem or postulate. Okay? Theorem or postulate. So this is the answer we're looking for. All right? So our answer is option number 4. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found this presentation beneficial to you, we'll like your positive feedback by giving us a thumbs up. Don't forget to subscribe to our channel for updates to the remainder of this review series and other great math tutorials. If you have any questions or need any support with the geometry section of the Regents exam, just ask us a question in the comment section below, and we'll be glad to address it as soon as possible. More clips can be found on mathgotserved.com. Thanks again for watching. Have a wonderful day.